In Module 15E, we're going to start discussing reaction mechanisms. What is a mechanism and how can we determine the mechanism? You need to understand what is meant by mechanism of a reaction, and you need to be able to understand terms like elementary step, rate determining step, and reaction intermediate. You also should be able to determine the molecularity of an elementary step and be able to verify whether a proposed mechanism agrees with the experimentally determined rate law. Again, rate laws, we always get them from experiment, but we can predict what they are and compare and say, does this back up our data? Does it mean it's the right rate, the right mechanism? No, it doesn't guarantee it. It just supports that belief. Reaction mechanisms themselves. So why are we studying kinetics again? We asked this at the very beginning of this chapter. The reason we study chemical kinetics is to determine the reaction mechanisms. This is the most important reason to study reaction mechanisms. A reaction mechanism itself is a sequence of events leading to the overall chemical change. It's how things are happening, what particles are coming together, how they're reacting, what's happening in solution at a molecular level, allowing the overall reaction to occur. Within this, we've got an elementary reaction or elementary step. This is where the particles themselves collide. We also have molecularity, which tells us how many particles are involved in an elementary reaction. So an overall reaction that we talk about, like we've written reactions, you guys have written reactions for months at this point. But sometimes when we write a reaction is the overall reaction. It's not actually how they occur in their individual steps. Sometimes it is, sometimes it isn't. An elementary reaction is the actual individual particles that are coming together, what's reacting in what order, and how does that work. Sometimes the reaction has one step, period. Sometimes it has a series of elementary steps that all add up to the overall reaction that we've written. The molecularity is how many particles are involved in each elementary step. We can have unimolecular, which is involving only one particle itself. Bimolecular is an elementary reaction that involves the collision of two particles. There's even termolecular, which is an elementary reaction involving the collision of three particles. But this is very rare. Why is it very rare? Well, because for something to react, for three particles to come together and react, we're going to talk about the collision model in a coming module. But what we find is that particles in the elementary steps, particles have to come together in the right orientation and at the right speed to actually react. The chances for three molecules to come together, all oriented perfectly in the right orientation and at the right speed for a reaction to occur, just not as common. But unimolecular, bimolecular, and sometimes termolecular do occur. The important thing here, you cannot get the rate law from the overall balanced reaction or equation. It is not possible. You can, however, get the rate law from an elementary reaction or an elementary step. So looking at reaction mechanisms, these are the different types we have: unimolecular, bimolecular, termolecular. Unimolecular is just one single particle undergoing that reaction. So if we have reactant A going to products, we write the rate law for this as rate is equal to K times the concentration of A. It's unimolecular because it's one particle. Bimolecular, we have two options. We can have reactant A colliding with reactant B. This is a bimolecular because I've got two particles here. And this rate law here would be rate is equal to K times concentration of A times concentration of B. We could also have two molecules of A coming together. This is also bimolecular because it's two particles. They may be the same compound, but they're two different particles coming together. And the rate law would be written as rate is equal to the rate constant K times concentration of A squared. Hence, order of reaction with second order. And then termolecular, we have A plus B plus C going to products. The rate there would be K times concentration of A times concentration of B times concentration of C. We could also have something like A plus B going to products. Also termolecular, K is rate constant is equal to K times concentration of A squared times B. Or even less, you could also have A plus A going to products. That would also be termolecular. And the rate there would be K times A cubed. So, multi-step mechanisms. Reactions often occur in a series of elementary steps. Elementary steps are the individual steps that are actually occurring. We write the reaction as an overall reaction. But these elementary steps must satisfy two requirements. First, these elementary steps must agree with the experimentally determined rate law. Experiment always wins the game, right? So any elementary steps we create or we predict to try to describe a reaction must agree with what experimentation is actually showing us. Second, the addition of the individual elementary reactions must equal the overall balanced reaction. So let's look at some examples. Consider the reaction NO2 plus CO going to NO plus CO2. The mechanism for this reaction is believed to occur in the following steps. First elementary reaction, so these are two different elementary reactions. In the first step, I've got 2 moles of NO2 reacting to produce NO3 plus NO. I then have NO3 reacting with CO to produce NO2 and CO2. The first elementary step is called the slow rate determining step. The second elementary step is fast. Slow rate determining. There's a key there. That's what's going to help us determine the rate law. So, what rate law is consistent with this mechanism? The rate law is based on the slow rate determining step because it's the step that controls how fast the reaction goes, right? It's the rate determining. The rate law consistent with this mechanism would be rate equal to my rate constant K times NO2 squared. So it's the reactants in my rate determining step. This works because my rate determining step is the first step. It's a bit different when the rate determining step is not your first step. When the rate determining step is the first step in the reaction, the rate law consistent with that mechanism would be the rate law for that first elementary step. The experimental rate law for this reaction is rate is equal to K rate constant times NO2 squared. So I can say, is this reaction valid? Well, it's possible. We don't know. It is possibly valid. Because the rate determining step gives us a rate law that's consistent with what we find. And if I add these two reactions together, my NO3 cancels out. One of my NO2s cancel out on each side. Remember, reactants products cancel out. And I'm left over with NO2 plus CO, giving me NO plus CO2. So I've satisfied both requirements. My predicted rate law agrees with my experimentally determined rate law, and the sum of the individual elementary reactions equals the overall balanced equation. In this reaction, NO3 is called an intermediate, or a reaction intermediate. An intermediate is something that is produced in one step and consumed in a subsequent step. So it was produced, now it's being consumed. It's not there at the beginning of the reaction, it's not there at the end. That is an intermediate. So thinking about the same reaction still, what about this mechanism? NO2 plus CO giving me NO2 or NO plus CO2. What if I said this was just the one elementary step? What if this overall reaction was the entire elementary step as well? That is possible. So what if this was the rate determining step? Well, I would predict the rate here. to be equal to my rate constant K times NO2 concentration times CO. Is this possible? No, because I know the experimental rate law is K times concentration of NO2 squared. They don't match. So this is not possible. That tells me that it's not a one single step reaction. There's a series of elementary steps that go into this reaction occurring. What about this mechanism? If I had NO2 plus NO2 giving me NO3 plus NO, it is my fast step, and my slow step was NO3 plus CO giving me NO2 plus CO2. Here's the trick. When your slow step is the first step, it's really easy to find the rate. But when your slow step is your second step, it's not so easy. We got to do a little bit of mathematical manipulation here. So I'm going to erase some of this for some space. So if I was to write the rate law based on my slow step here, the rate there would be equal to K, my rate constant, times the concentration of NO3 times the concentration of CO. The issue is I am not allowed to have intermediates in my rate law. Why? Because they're produced and consumed in a reaction. They're not a reactant or a product. So I can't have them in my overall rate law. So I've got to find a way to substitute this in. If I look at my first reaction where the NO3 is actually produced, what I'm going to say is the rate going this direction is rate 1. The rate in the reverse direction is the rate minus 1. And I'm going to call this rate 2 just to keep them straight. Okay, so rate 2, K2. If I wrote the rate 1, this would be K times concentration of NO2 squared. If I wrote rate minus 1, K minus 1 times NO3 concentration times NO. But I'm going to assume that rate 1 is approximately the same as rate minus 1, the reverse reaction. It's a fast reaction. I'm going to assume that it's going to happen at approximately the same rate, which would allow me to say that K1 NO2 squared is equal to K minus 1 NO3 concentration, NO concentration. I'm then going to rearrange this equation to solve for NO3. So if I do that, I get K1 times NO2 squared divided by K minus 1 times NO. I'm then going to substitute this in for NO3. And I'm going to run out of room. So rate 2 is equal to K2 times K1 times NO2 squared over K minus 1 times NO times the concentration of CO. With this mechanism, this would be my predicted rate law. Does it match? Nope. Because experimental the rate was equal to my rate constant times NO2 squared. So the most simple way to do it was to make that first reaction the rate limiting step, and then it adds up to overall to what I find. Again, do we know that's the absolute reaction? No, we don't. We're predicting it based on what we observe. The mechanism for a particular reaction is believed to be as follows. H2O2 plus I minus giving me HO plus IO minus. IO minus plus H2O2 giving me I minus H2O and O2. The first reaction, we call these elementary steps again. The first reaction is slow, the second reaction is fast. When it says slow, that is your rate determining step. Write the balanced equation for this reaction. Each of these reactions add up to the overall balanced reaction. So I've got 2 moles of H2O2 let's see, I minus cancels with I minus. IO minus cancels with IO minus. And I've already written down my H2O2s. This reacts to produce 2 moles of H2O liquid plus O2 gas. Here's the trick. Another trick. Always tricks, right? This I minus here was present at the start and then regenerated. But I cut it out because it's on both sides, right? Not quite. It was present at the start and was regenerated. It means it is a catalyst. So what role does I minus play in this reaction? It is a catalyst. A catalyst is often consumed in one elementary step and then regenerated in a subsequent step. It's not in the balanced reaction because it's not per se a reactant, but the reaction won't go without it either. So when you send something like this, like I minus reactant and then regenerate as a product by the end of the reaction, you don't write it in the overall balanced reaction, but you do write it above the arrow to signify that it is in fact a catalyst. What role does I minus play? I minus is an intermediate. How do I know the difference? Because I minus was generated or produced during the reaction and then consumed. I minus was consumed then produced. IO minus was produced then consumed. So what is the rate determining step in a reaction here? This is called a reaction profile. It shows you the reaction progress versus energy. We see reactants versus products. Overall, the reactants are a higher energy state than the products, which means this is an exothermic reaction. So delta H would be negative. We release energy. But I can't just go from reactants to products. I have to go through these transition states. I've got a transition state here and a second transition state here. E sub A is your activation energy. It's the energy that is required to go through that transition state. How do I know which one's my rate determining step? In this one, it's EA1. I see the transition state is higher for my first activation energy than my second. And in between the two states, I see this little purple box, or this lowering of the energy levels right here. This lowering spot is an intermediate that has been created. It's an intermediate step between the two elementary steps. So this is elementary step 1. And it happens to be the rate determining step. This is elementary step 2. and it is fast. So, for the reaction, 2Fe2 plus Cl2 minus, or plus Cl2, give me 2Cl minus plus 2Fe3 plus. If the experimentally determined rate law is as follows, the rate is equal to the rate constant K times Fe2 plus times Cl minus, propose a mechanism. Well, the rate tells me what my slow rate determining step is. The rate is telling me that I've got Fe2 plus reacting with Cl2 to produce something. I'm going to have a second reaction, maybe a third, and overall, they're going to add up to my overall reaction. So 2Fe2 plus Cl2 aqueous, giving me 2Cl minus plus 2Fe3 plus. And overall, I have to add up to that, right? Well, I've only used up one Fe2 plus, and I've got to have two. So there must be another one here. Then what's going to happen? Well, Fe2 plus Cl minus, I know I need to make some Fe3 plus. I only have one Fe here, so there can only be one Fe3 here. So there must be an Fe3 plus here as well, because I've got two of them here. I've got to be able to produce some Cl minus because I've got two of them here. But if I took Fe2 plus and reacted it with Cl minus, one electron is going to be exchanged here. That's the one electron there, which means what's left is Cl. I don't have Cl in my overall reaction though, so Cl must be an intermediate so it can cancel out. Fe2 plus Cl, giving me Fe3 plus Cl minus, exchange of one electron again. This would be my slow rate determining step. This would be my fast step. Again, how did I know this? Well, I know that I've got Fe2 plus and Cl2 reacting because that's my experimental determined rate law. So that can be the only reactants I have in my slow rate determining step. I'm going to assume that step is first. Does that mean that this mechanism is valid? No, it means this mechanism is possible. It does not prove it is the only mechanism that's possible. But I see this, and then I say, okay, well, I've got to form Cl minus and Fe3 plus. If I form an Fe3 plus a Cl minus, I can only have one Fe3 plus. I only have one Fe here. So I can only have one Fe here. Iron has lost one electron, so it must have given that electron to chlorine, right? Gave that electron to chlorine, I've got one Cl minus. What's left over if I have one Cl minus? A Cl. I still need another Fe2 plus for my overall balanced reaction, but I've got to find a way to get rid of Cl because there's no Cl in my reaction. Overall reaction's got to be intermediate. Fe2 plus Cl. If that Fe2 plus gives one electron away, it forms Fe3 plus and Cl minus, and when added up together, I get my overall balanced reaction. What about this one? What's the rate law for the following elementary reaction? Cyclopropane versus propylene. Students get very stressed out by this one. They immediately look at this, they see structures, they get very stressed out, they don't know what to do. Totally understandable. This is what's called isomerization. And I can't spell. Meaning same molecular formula, but different connectivity. The rate here, K times the concentration of cyclopropane. It tells me here this is an elementary reaction, which means this is all that I have. This is a slow rate determining step, which means that the rate is just going to be equal to the concentration, to the rate constant times concentration of cyclopropane that I have. and it's just going to rearrange itself into propylene. Mechanisms of the fast initial step. We did an example like this a few minutes ago when we were talking about the different possible mechanisms. Let's do another one. In order to determine the rate law for a mechanism where the first step is a fast step, that is not the rate determining step. The key is that the rate law must not contain any reactive intermediates. So if I look at the reaction of 2 moles of NO plus 1 mole of O2, give me 2 moles of NO2. It's believed to occur by the following mechanism. Step 1, NO plus O2 in equilibrium with NO3, and that's a fast step. Step 2, NO3 plus NO in equilibrium with 2 NO2, that is a slow rate determining step. I want to know what rate law is consistent with this mechanism. From the rate determining step, I would say here, the rate is equal to K, I'm going to call this 2 since it's step 2, K2 times NO3 concentration times NO. But again, this isn't allowed because I cannot have reactive intermediates in my rate law, and that is definitely reactive intermediate. So from step 1, I'm going to say that the rate 1, so the rate of the forward reaction, would be equal to the concentration of NO times the concentration of O2. Rate minus 1 would be the reverse direction. And that would be equal to K times NO3. The key idea here we assume rate 1 is approximately equal to rate 2, or sorry, rate minus 1. So the forward reaction is approximately equal to the reverse reaction. Is that possible? Well, it's a fast step, so yeah, it's possible. If we assume that, then we can set those two equal to each other. We can say K1 and NO2 is equal to K minus 1 NO3. I then can solve for the reactive intermediate. And plug that in to my rate based on the second step. Which I can then simplify and say, because I have 2 NOs there, rate 2 is equal to K2, that should be a minus 1, divided by K1. Sorry, I'm running out of space, and this is actually a problem. Hold on. Let me move this up. Move this up so I can actually fit this in here. And I'm going to change the color so you guys can see it a little bit better. Rate 2. I'm going to write K2, K1, divided by K minus 1, times the concentration of NO, quantity squared, times O2. This is a valid rate law for this mechanism. Remember, when you're doing mechanisms, if the first step is your slow step, it's pretty straightforward. You can write your rate law based on that first rate determining step. Keywords, rate determining step. But if the first step is fast, you have to do some kind of workaround because you cannot have reactive intermediates in the rate law. They're just not allowed.